In this program, I want to take a look at a few shortcuts that we can employ when we use the ICE table to solve equilibrium problems. So in my first problem, I've got the starting concentrations, so that saves me a step. I don't need to determine them, of all three species. So I have all three of them present in my container. So I have full knowledge of the initial concentrations. Nothing in here about the change, nor anything really about what concentrations are at equilibrium. The constant does give me a little bit, though, knowledge about what should be present at equilibrium. That large value suggests favoring products. Right now I have equal amounts, and at equilibrium I know that the reaction is going to shift forward. So this is going to have to probably go up, and these two down. I'm going to introduce the variable x to represent what the change is in hydrogen, and that means that iodine in a 1-to-1 ratio must change by the same amount. Hydrogen iodide, which is a 1-to-2 ratio, must change by twice that amount. So at equilibrium, I have these expressions. Now let's turn to the equilibrium constant and its expression. So we know that at equilibrium the concentration of hydrogen iodide squared over hydrogen times iodine must equal 49. So let's put in the values. So we know that this is 49.6. This is 0.5 plus 2x squared, and the bottom 0.5 minus x for the hydrogen, and it's the same thing for iodine, so also squared. Now, we could solve this by expanding these two expressions, turning them into quadratics, and then isolating and ending up with the quadratic formula to solve. But here's our shortcut. I recognize here that these are perfect squares, so I'm going to take the square root of this side and the square root of this side. That gives me 7.04, 0.5 plus 2x, and 0.5 minus x. Now I won't have a squared term to deal with. Multiplying both sides by this expression, so I'll continue that up here, gives me 3.52 minus 7.04x has to equal 0.5 plus 2x. Bringing this over to this side, and then taking this over to this side. Now I'm solving just for x by dividing both sides by 9.04, and you get 0.33. Now we're not quite done. All we've done here is determine x. What it wants is the concentrations at equilibrium. So I've got to take this back to my equilibrium line and substitute in for x. And when I do that, I'll get the concentration of hydrogen will equal the concentration of iodine, which will equal 0.33 moles per decimeter cubed. And substituting in 2 times 0.33 plus 0.5, that'll give my hydrogen iodide concentration is 1.66 moles per decimeter cubed. So be aware of the shortcut of taking the square root of both sides to avoid the use of the quadratic formula. And this question will show us another trick we can use to solve these problems. In this one I'm given the moles in a container, so I have to convert this to get the initial concentrations by dividing by the volume. So this would be 0.25, 0.42 divided by 2, 0.21, and these are only present, so that'll be 0, that'll be 0. Now information about change in equilibrium. Much as before, there's no direct information about change nor the equilibrium amounts, so I'll turn to the constant. Now this is a small constant, suggesting we favor our reactants, but the fact that we have no products tells me this reaction has only but one way to go. It has to make some of this before you can reach equilibrium. So these two have to go up ever so slightly, and these will both go down. And I'll let the change here be x, and a 1 to 1 to 1 ratio across the board suggests that these changes will all have a value of x. So at equilibrium, I'll have x and x of this, 0.21 minus x, and 0.25 minus x. We'll turn now to the equilibrium expression. It says I need the concentration of hydrogen times the concentration of nitrogen dioxide divided by nitrogen monoxide and my water vapor. Now, putting in the values that we've got 1.18 times 10 to the minus 4. On the top, I have x times x, and on the bottom, 0.25 minus x, 0.21 minus x. Now again, expanding these terms and isolating for x suggests we are headed towards the quadratic formula again, and here's the shortcut. Again, I take a look at this constant. Being so small, that suggests in this situation that the reactants are going to be at a much, much greater concentration than my products. In other words, the change is going to be small. That means x isn't going to be particularly large. And to do the simplification I'm going to make then is that if x is small, at equilibrium, the concentration of nitrogen monoxide is going to be almost the same number. Similarly here, this isn't going to change by much. My reactants change will be small. And typically you can use this shortcut when you have something like 10 to the minus 4 as the exponent, or smaller. That then simplifies the bottom part of my expression. I can essentially just make it 0.25 and 0.21. This will then avoid the use of the quadratic in solving this expression. So now, when I expression, I'm going to have x squared on this side, 1.8 times 10 to the minus 4, and it'll be multiplied by 0.25 and 0.21, and that's going to equal now x squared. So again, I've gotten rid of that term, and taking the square root of both sides and solving then for x, I get like 0.0031. Indeed a fairly small number. If you did leave x in here and solve with these in this form, you would employ the quadratic formula and you would solve. And the answer you actually get then is closer to 0.0030. So you would get that if you kept those numbers in. So you can see that you're off slightly using this shortcut, but not enough to worry about. So at equilibrium then, the concentration of hydrogen equals the concentration of nitrogen dioxide, which is roughly 0.0031 moles per liter, and these two concentrations haven't changed by much. So if I even if I put this small value in here, I still don't get much of a change. So the concentration of nitrogen oxide stays virtually the same, and the concentration of the water vapor the same as it started. So when you have very, very small equilibrium constants, That suggests that the change in your reactants will be extremely small and you can neglect them, and it makes it a little bit easier to solve your problem. So those are a couple of shortcuts you should be aware of. In our final program, we'll take a look at Gibbs free energy and its relationship to the equilibrium constant. Thanks for watching.